Hello and welcome. Tonight, we'll be exploring a question that seems almost too simple to deserve much thought. Why doesn't Earth fall into the sun? It is the kind of question that many of us quietly accept without ever truly asking. We learn that gravity pulls objects together. We watch an apple fall from a tree, rain drift gently toward the ground, and a dropped cup tumble from our hands. Again and again, our everyday experience teaches us the same lesson. Things that are pulled eventually fall. And yet, somehow, our entire planet appears to ignore that rule. The sun is unimaginably massive. Its gravity reaches across millions of kilometers, holding together an entire family of planets, moons, comets, and asteroids. If gravity is always pulling Earth inward, then why has our world not disappeared into the sun long ago? The answer is both surprisingly simple and wonderfully strange. By the end of our journey tonight, you may discover that Earth has not escaped gravity at all. In a quiet and beautiful way, it has been falling this entire time. Before we can understand that idea, though, we need to gently set aside one habit of thinking that has followed us since childhood. Nearly every experience you have ever had takes place on the surface of Earth. Here, down feels obvious. It is the direction toward your feet. Up points toward the sky. We rarely question these directions because they seem as permanent as the ground beneath us. But the moment we leave our familiar world, something unexpected happens. The universe has no universal up. It has no universal down. Those ideas belong only to places where gravity gives us a convenient sense of direction. Out among the planets and stars, those directions quietly disappear. There is only distance, motion, and the relationships between objects moving through an enormous cosmos. This is one of those ideas that sounds simple when spoken aloud, yet takes a little time to truly settle into the imagination. Imagine drifting alone in the quiet darkness between the stars. Without a nearby planet beneath your feet, where would down actually be? Turn slowly, rotate in any direction. Nothing changes. There is no invisible arrow pointing toward the bottom of the universe. The universe simply does not work that way. Once that familiar idea of down fades away, another question naturally begins to emerge. If there is no down in space, then what does it really mean to say that something is falling? That question will quietly guide us through everything that follows. There is another curious experience that is happening to all of us right now. Although it feels as if you are sitting perfectly still, you are moving through space at an astonishing speed. The chair beneath you feels steady. The room seems peaceful. Perhaps the only motion you notice is the slow rhythm of your breathing. Yet beneath that calm surface, Earth is carrying you on an extraordinary journey. Every second, our planet travels many kilometers around the sun. At the same time, Earth is rotating, gently turning day into night. The sun itself is also traveling, circling the center of our galaxy. And our galaxy, together with countless others, continues its own vast voyage through the expanding universe. Motion exists within motion, journey inside journey, like layers of gentle waves crossing an endless ocean. Strangely, we feel almost none of it. That may seem impossible at first. How can something move so quickly without us noticing? The answer is actually something you have experienced many times before. Imagine sitting comfortably inside a smooth train. At first, you notice the moment it begins to move. There is a gentle push, a slight change in balance. But once the train reaches a steady speed, something remarkable happens. You stop feeling the motion itself. You can read a book, sip a warm drink, or simply gaze out of the window while the countryside quietly slips past. The motion has not disappeared, only the sensation of changing motion has. An airplane offers a similar experience. After climbing through the clouds, it settles into a smooth cruise. For hours, passengers walk through the cabin, enjoy a meal, or even fall asleep, often forgetting they are traveling hundreds of kilometers every hour. Earth offers us the same quiet illusion, only on a far grander scale. Because everything around us shares the same journey, the motion itself becomes almost invisible. The oceans move with us. The mountains move with us. The atmosphere moves with us. Even every cell inside your body shares this silent voyage. Nothing around us is being left behind. Everything is traveling together. Perhaps this is why the universe often feels so much calmer than it truly is. What appears perfectly still may actually be moving with extraordinary grace. This gentle realization begins to reshape the question we asked only a few moments ago. Perhaps the mystery is not why Earth refuses to fall. Perhaps the mystery is whether our understanding of falling has been incomplete all along. Our everyday intuition tells us that falling always ends with a collision. A leaf reaches the ground. A stone lands beside a river. A raindrop finds the earth below. Every fall seems to have a destination. But what if there were another kind of falling? A fall so perfectly balanced that it never reached the ground. A fall that could continue hour after hour, year after year, even for billions of years. It sounds almost impossible, almost like a quiet contradiction. And yet this strange possibility lies at the heart of our solar system. The planets are not hanging motionless around the sun. They are not suspended by invisible strings, nor are they constantly pushing themselves away from its gravity. Instead, they may be doing something far more elegant, something that is both wonderfully simple and deeply surprising. To discover it, we only need one small thought experiment, not with a planet, not with a spacecraft, but with something as ordinary as a ball thrown from the top of a very high mountain. Perhaps, hidden inside that simple throw, is the first glimpse of why an entire world can spend billions of years falling without ever arriving. The idea that Earth may be falling without ever reaching the sun sounds almost impossible at first. After all, every fall we have ever witnessed eventually comes to an end. A leaf settles onto the grass. A raindrop reaches the ground. A stone thrown into the air always finds its way back home. Our experience quietly teaches us that falling and arriving belong together. But nature has a gentle habit of surprising us whenever we begin looking just a little farther than our everyday lives. Imagine standing on top of an impossibly high mountain, not the tallest mountain on Earth, but one so high that the air has almost disappeared, where the sky has already begun to fade into the darkness of space. In your hand is a small metal ball. Nothing extraordinary, just something small enough to throw with one arm. You throw it straight forward, not upward, not downward, simply forward. At first, the story unfolds exactly as you would expect. The ball flies through the air. Gravity quietly pulls it downward. After a short journey, it strikes the ground. Nothing mysterious has happened. Now imagine throwing it a little harder. This time, it travels farther before touching the ground. Gravity is still pulling on it every moment. That has not changed. The only difference is that the ball keeps moving forward for a longer time before its fall is complete. Now imagine throwing it harder still. Again, it travels even farther. Each time you give it a little more speed, something curious begins to happen. The ground beneath it seems to stay just a little farther away. Of course, the ground is not actually moving. It only appears that way because Earth itself is curved. While the ball is falling, the surface of our planet is quietly curving away beneath it. Most of the time, we never notice this. Earth is simply too large. Its gentle curve hides itself from our daily lives. But from the top of this imaginary mountain, the effect slowly begins to reveal itself. Now let your imagination take one final step. Suppose you could throw the ball not just harder, but fast enough that every meter it falls is matched by another gentle curve in Earth's surface. The ball continues falling. The planet continues curving away beneath it. Again, and again, and again. The ball never stops falling, yet it never reaches the ground. It simply keeps missing it. This simple thought experiment became one of the most famous ideas in the history of science. It is often called Newton's cannon, not because anyone intended to fire a cannon around the world, but because it revealed something extraordinary hiding inside an ordinary fall. An orbit is simply a fall that never finds the ground. Once this idea settles into your mind, the solar system begins to look completely different. The moon is falling toward Earth. Earth is falling toward the sun. Even many satellites surrounding our planet are doing exactly the same thing. None of them are escaping gravity. None of them are floating because gravity has somehow disappeared. Gravity is doing precisely what it has always done. It is quietly pulling. The difference is that these worlds and satellites are already moving sideways so quickly that they keep missing the place where gravity is guiding them. Perhaps another image can make this even easier to picture. Imagine skipping a smooth stone across the surface of a quiet lake. Each bounce carries it farther than the last. For a brief moment, the stone seems to resist sinking. It is not because gravity has stopped working. Gravity remains patient throughout the entire journey. The stone simply keeps moving forward, while gravity gently pulls it downward. An orbit is not exactly like a skipping stone, but it shares the same beautiful balance between forward motion and aims. There is another misunderstanding that quietly slips into many people's imagination. Sometimes we picture a planet as though it were carefully balancing between two equal forces, one force pulling inward, another somehow pushing outward. It is an understandable picture, but nature is even simpler than that. There is no mysterious outward force constantly pushing Earth away from the sun. Instead, Earth simply continues moving in the direction it was already traveling. This quiet tendency is one of the most natural behaviors in the universe. If nothing changes a moving object's path, it simply keeps going. You have experienced this yourself many times. Slide a book gently across a smooth table. It continues moving until friction gradually slows it down. Roll a ball across a polished floor. It keeps traveling until something changes its motion. Objects do not naturally seek rest. They naturally continue what they are already doing. Space happens to offer almost no friction at all. Nothing is rubbing against Earth as it travels around the sun. Nothing is acting like invisible air resistance. Our planet simply continues its ancient journey, while gravity quietly bends that journey a little every moment. Not enough to pull Earth directly inward, not too little to let it wander away, just enough to create an endless curve. This is why an orbit should never be imagined as a planet standing still while gravity holds it in place. Nothing is standing still. Everything is moving. Everything is changing direction, ever so gently, every second. From our point of view, the orbit looks calm, predictable, almost peaceful. Yet beneath that calm appearance lies one of the most graceful motions in nature, an endless fall. It is remarkable that such an elegant idea can emerge from something as ordinary as throwing a ball. Sometimes the universe hides its deepest truths inside the simplest images. The same principles that guide a child's throw across a field also guide the dance of planets around stars. But this beautiful explanation naturally raises another question. If Earth continues falling because gravity gently bends its path, then what exactly is gravity? What is this quiet influence that reaches across empty space, guiding worlds without touching them? For more than 2 centuries, one remarkable thinker offered an answer so powerful that it transformed humanity's understanding of the heavens. And even today, his ideas continue to guide spacecraft across the solar system with extraordinary precision. The story now begins to widen, reaching from a falling apple to the graceful motion of every planet beneath the stars. Long before anyone understood why Earth circles the sun, people looked upward with a mixture of wonder and uncertainty. The heavens seemed different from everything below. On Earth, things changed. Leaves fell, rivers flowed, people grew older, buildings slowly crumbled beneath wind and rain. But the sky appeared untouched. Night after night, the stars returned to familiar places. The moon followed its quiet rhythm. The planets wandered across the darkness in ways that seemed mysterious, almost alive. For thousands of years, many believed that two completely different sets of rules governed the universe. One belonged to Earth, the other belonged to the heavens. It was an understandable way of seeing the world. After all, nothing about everyday life suggested that a falling stone and the moon overhead could possibly have anything in common. Then, during the 17th century, a remarkable idea began to emerge. It did not begin with a telescope pointed toward distant planets. It began with a question. Could the same rule explain everything? Not just one falling object, not just one planet, everything. The man who would eventually answer that question was Isaac Newton. His name has become so familiar that it is easy to forget just how revolutionary his ideas once were. Newton did not simply explain why apples fall. He connected Earth and the heavens into a single story. According to a famous tale, Newton was sitting beneath an apple tree when he watched an apple fall to the ground. Whether every detail of that story is perfectly true matters less than the question it represents. Why should the apple fall downward? And if something on Earth can be pulled toward the ground, could the moon also be falling toward Earth? It was an astonishing thought, not because anyone had seen the moon falling, but because no one had imagined that the same invisible influence could reach both a small apple and an object nearly 400,000 kilometers away. Newton realized something extraordinary. The force pulling the apple downward did not suddenly stop at the top of the atmosphere. It continued outward, far beyond the clouds, past the moon, beyond the planets, into the enormous darkness of space. Gravity was not simply an earthly phenomenon, it was universal. Suddenly, the universe became beautifully connected. The apple, the moon, Earth, Jupiter, a distant comet, they were all participating in the same invisible conversation. That single realization changed science forever. For the first time, the heavens were no longer a separate kingdom governed by mysterious rules. The same universe existed everywhere. The same quiet law reached across both the smallest moments of everyday life and the grandest motions of the cosmos. Perhaps that was Newton's greatest achievement. He did not divide nature into separate stories. He united them. There was another mystery that Newton helped people understand. If gravity is always pulling Earth toward the sun, why does Earth continue moving around it instead of falling directly inward? At first glance, it seems as though something must be constantly pushing Earth away. But nature, once again, turns out to be wonderfully economical. Nothing needs to push Earth outward. Instead, Earth simply continues moving in the direction it was already traveling. Imagine gently rolling a glass marble across a perfectly smooth floor. If the floor were completely frictionless, the marble would continue gliding long after it left your hand. Not because an invisible force keeps pushing it, simply because nothing is stopping it. Or picture an ice skater drifting across fresh ice after one graceful push. For a few peaceful moments, no additional effort is needed. The motion simply continues. Space is even quieter than polished ice. There is almost nothing there to slow a planet down. Earth has been carrying its forward motion ever since the earliest days of the solar system. Gravity does not erase that motion. It gently reshapes it. Every moment, Earth continues moving forward. Every moment, the sun's gravity bends that forward journey ever so slightly inward. Neither wins. Instead, together they create something entirely new, a graceful curve, a repeating path, an orbit. It can be tempting to imagine this as a tug of war, with two equal forces pulling against one another. But that picture quietly misses the elegance of what is really happening. One side is not a force at all. It is simply motion continuing naturally. The other is gravity, patiently changing the direction of that motion without bringing it to an end. If you have ever watched someone swing a small stone tied to a string, you have already seen a familiar pattern. The stone constantly tries to move forward. The string gently changes its direction. The result is not a straight line, it is a circle. Of course, Earth is not attached to the sun by any invisible string. The comparison is only meant to help us picture something our eyes cannot directly see. Nature often allows simple images to illuminate deeper truths. Newton's ideas also helped explain something astronomers had already observed many years earlier. A German astronomer named Johannes Kepler had carefully studied the paths of the planets. From years of patient observation, he discovered elegant mathematical patterns describing how planets move around the sun. His descriptions were astonishingly accurate, yet they left an important question unanswered. Why? Why should planets move that way in the first place? Newton provided the missing piece. Gravity supplied the reason hidden beneath Kepler's beautiful observations. The planets were not following mysterious celestial habits. They were responding to the same universal influence that guided every falling object on Earth. This was one of the greatest moments in the history of science. Observation and explanation finally met. The sky became something humanity could understand, rather than simply admire. Even today, centuries later, Newton's work remains astonishingly successful. Engineers still rely on his ideas to guide satellites into orbit. Space agencies still use them to calculate journeys to the Moon, Mars, and far beyond. His picture of gravity continues to describe most of the motions we observe throughout the solar system with remarkable precision. For many people, this might sound like the end of the story. Gravity pulls, planets move, mystery solved. But Newton himself understood that one question still remained. Perhaps it was the deepest question of all. He had described what gravity does with extraordinary accuracy. He could predict the motion of planets. He could explain the dance of moons and comets. Yet he could not explain how gravity actually works. How could the sun influence Earth across nearly 150 million kilometers of what carried that influence? What connected them? Newton openly admitted that he did not know. It was one of the rare moments when one of history's greatest scientific minds looked into the unknown and simply said, in effect, "This part remains a mystery." For more than 200 years, that mystery quietly waited. Then another young thinker began asking questions that seemed almost impossible. What if gravity was not truly a force reaching across space at all? What if space itself had been part of the answer from the very beginning? For more than 200 years, Isaac Newton's description of gravity stood as one of humanity's greatest achievements. It explained the motions of the planets with astonishing accuracy. It predicted the return of comets. It helped astronomers calculate eclipses years before they happened. Centuries later, engineers would still rely on Newton's equations to send spacecraft toward distant worlds. It seemed that gravity had finally been understood. And yet, hidden beneath all of that success, one quiet question refused to disappear. Newton had explained what gravity does. He had never explained what gravity is. How could the sun influence Earth across such an enormous distance? Nothing visible stretched between them. No rope, no beam of light, no invisible chain. The sun simply seemed to know where Earth was, and Earth seemed to respond instantly. Even Newton himself admitted that this troubled him. He was comfortable describing nature with extraordinary precision. He was less comfortable pretending to know something he did not. Sometimes, the greatest scientists are remembered not only for the questions they answered, but also for the questions they had the courage to leave unanswered. More than 2 centuries passed before another remarkable mind looked at the same mystery from an entirely different direction. Albert Einstein was not trying to improve Newton's mathematics. In many situations, Newton's description already worked beautifully. Instead, Einstein asked a far more unusual question. What if gravity is not really a force in the way we imagine it? At first, that idea almost sounds unreasonable. If gravity is not pulling things, why do objects fall? Why do planets remain in orbit? Why do we stay firmly on Earth's surface? The answers begin with something so ordinary that most of us hardly notice it. Imagine walking through a quiet park after a gentle snowfall. Fresh snow covers everything. Across the smooth white surface, people have already begun to leave footprints. Some paths are narrow, others are wider, where many feet have passed before. Without thinking very much, you naturally choose one of those paths. Not because anyone pulls you toward it, not because someone is giving directions. The path simply offers the easiest way forward. Now imagine a small stream flowing across a hillside. The water does not stop to decide where it should go. It follows the shape of the land. Every curve, every gentle valley, every quiet slope, the landscape guides the water without ever touching it. Or picture a marble resting near the edge of a smooth wooden bowl. The moment you release it, the marble begins to move. Not because the bowl is reaching out to grab it, not because invisible hands are pulling it. The marble simply follows the shape beneath it. Its path is guided by the surface itself. Einstein began wondering whether the universe might work in a surprisingly similar way. Perhaps planets are not being pulled through empty space. Perhaps space itself possesses a shape. Perhaps that shape quietly guides every object along its journey. This was an extraordinary leap of imagination. For generations, people had thought of space as an empty stage. The stars, the planets, the galaxies, they were the actors. Space merely provided the empty background. Einstein proposed something completely different. The stage itself could change. It could bend. It could stretch. It could influence the actors moving across it. This idea feels unfamiliar because our senses never directly reveal it. We cannot see space. We cannot touch it. We cannot watch it bend with our own eyes. Yet many important things in nature remain invisible until we learn how to recognize their effects. You cannot see the wind itself. You only notice leaves beginning to dance. You cannot see music floating through a room. You only hear the gentle vibration reaching your ears. Likewise, we do not directly observe the shape of space. We observe the graceful motions that its shape quietly creates. Only after building this picture does it become helpful to introduce the scientific name. Physicists call this idea curved spacetime. It may sound like a complicated expression, but the picture behind it is surprisingly gentle. Space and time are not completely separate. Together, they form the quiet fabric within which everything in the universe exists. Stars move within it. Galaxies drift through it. Light itself travels across it. And wherever enough matter gathers, that fabric changes its shape. Imagine laying a soft blanket across a wide bed. At first, the blanket lies smooth and flat. Now place a heavy book near its center. The blanket sinks slightly beneath the weight. Nothing tears, nothing breaks. The surface simply changes shape. That familiar image has helped generations of students picture Einstein's idea. It is useful, though it is not perfect. Unlike the blanket, space does not sag because another force is pulling it downward. There is no hidden flaw beneath the universe. The comparison simply helps us imagine that space can have a shape rather than being perfectly flat. Perhaps an even gentler picture is to think of a broad valley. After a spring rain, countless tiny streams begin flowing across the landscape. Each drop of water naturally follows the contours already present. None of the drops need instructions. None of them make conscious choices. The land quietly guides them. Einstein believed planets behave in much the same way. Earth is not constantly steering itself around the sun. Instead, it follows the gentle contours created by the sun's enormous mass. Many years after Einstein introduced this revolutionary picture, the American physicist John Wheeler found a wonderfully simple way to describe it. His words have become famous because they transform a difficult scientific idea into a sentence that almost anyone can picture. Matter tells spacetime how to curve. Spacetime tells matter how to move. There is a quiet elegance in those few words. The sun does not reach across space with invisible ropes. Earth does not struggle to resist being pulled inward. Instead, The presence of the sun gently shapes the surrounding geometry of the universe, and Earth faithfully follows that geometry. In a sense, the planet is not fighting gravity at all. It is simply traveling along the easiest path available. That realization changes the meaning of our original question. We began by asking why Earth does not fall into the sun. Now we are beginning to ask a different question. If space itself quietly guides Earth's motion, what kind of path is our planet actually following? At first glance, that path appears curved. Yet, in one of the most beautiful surprises of modern physics, Einstein would argue that Earth is following the straightest route it possibly can. It is that gentle idea will carry us into one of the most elegant concepts in all of science. It is a concept that pilots unknowingly rely on, that astronauts experience every day, and that quietly shapes the journey of every planet beneath the stars. Once you begin thinking of space as something with shape rather than empty nothingness, a surprising question quietly appears. If Earth is not being pulled around the sun by an invisible rope, then what exactly is our planet doing? The answer is wonderfully simple. Earth is following the straightest path it can. At first, that sounds impossible. After all, when we look at diagrams of the solar system, Earth's orbit is clearly curved. How can something curved possibly be straight? The answer depends entirely on the landscape through which that journey takes place. Imagine that you are standing in a large open field. Your friend is waiting on the opposite side. The shortest path between the two of you is obvious. You simply walk in a straight line. Now imagine something different. Instead of an open field, you are standing on the surface of Earth itself. Your friend is not a few hundred meters away. Instead, they are waiting on the opposite side of the planet. If you could somehow look at your journey from far out in space, your path would appear to curve gently around Earth's surface. But while you are actually walking, something very different is happening. You never feel yourself making a constant turn. You simply keep walking forward, step after step. The curve belongs to the world beneath your feet, not to the way you are choosing to move. Pilots have quietly relied on this idea for generations. Imagine looking at a map of Earth. Many long-distance airline routes appear strangely curved. A flight from North America to Europe often bends far toward the north. Another journey across the Pacific seems to arc gracefully over the ocean. At first glance, those routes almost look inefficient. Why not simply draw a perfectly straight line? The answer is that the map itself is slightly deceptive. Earth is round. A flat map gently stretches and reshapes its surface. The route that looks curved on paper is actually the shortest possible path across the globe. Without realizing it, pilots have been following nature's preferred paths all along. Mathematicians and physicists eventually gave these natural paths a name. They are called geodesics. The word may sound unfamiliar, but the idea behind it is surprisingly peaceful. A geodesic is simply the straightest possible path through whatever landscape you happen to be traveling. On a flat surface, a geodesic is exactly what you would expect. It is a straight line. On the curved surface of Earth, that same idea becomes a gentle arc. And within the curved fabric of space itself, a geodesic may become something we recognize as an orbit. Notice how different this picture feels from the one many of us first learned as children. Instead of imagining gravity constantly pulling Earth away from its natural path, we begin to see something much quieter. Earth is already following its natural path. It is simply that the universe itself is no longer perfectly flat. Perhaps another image can make this even easier to imagine. Picture a quiet river flowing through a broad valley. The water twists gently from side to side. From high above, the river seems to wander. It curves, it bends, it changes direction again and again. Yet the water itself is not making complicated decisions. Each tiny drop simply follows the landscape beneath it. The valley quietly determines the journey. Einstein believed planets behave in much the same way. Earth does not wake up each morning and decide where it should travel. It does not steer left or right. It simply follows the geometry already present around the Sun. The path appears curved because the universe itself possesses a subtle shape. This idea leads naturally to another surprising realization. If Earth is following the straightest path available, then perhaps falling itself deserves a new definition. For most of our lives, we have imagined falling as something that interrupts ordinary motion. A book resting on a shelf begins to fall only after someone removes the support beneath it. A leaf begins to fall only after it lets go of the branch. Falling seems like something unusual. Einstein quietly turned that picture upside down. Perhaps falling is not the interruption. Perhaps falling is the most natural motion of all. Imagine stepping into an elevator. For a moment, imagine something impossible. The cables disappear and the elevator begins falling freely. Inside, something remarkable would happen. You and the elevator would fall together. A book, released from your hand, would no longer drop toward the floor. Instead, it would quietly float beside you. Not because gravity had vanished. Gravity would still be present. In fact, gravity would be the very reason the elevator was falling. Everything inside would simply be sharing exactly the same journey. Einstein realized that this strange thought experiment revealed one of nature's deepest secrets. When everything falls together, gravity becomes almost impossible to notice. That same quiet idea appears hundreds of kilometers above Earth. Astronauts aboard the International Space Station often seem to float effortlessly through the cabin. Children sometimes imagine that they are far enough away for gravity to disappear. It is a comforting picture, but it is not quite true. Earth's gravity is still very much present there. Without it, the station would simply drift away into deep space. Instead, both the astronauts and the station are continuously falling around Earth together. Just like Newton's imagined cannonball, just like our own planet falling around the Sun, they keep missing the ground, again and again and again. That is why they appear weightless, not because gravity has stopped working, but because everything nearby is sharing the very same fall. You may even have experienced the smallest hint of this feeling yourself. A roller coaster begins its first great descent. For just an instant, your stomach seems to float, or perhaps an airplane passes gently through a pocket of descending air, and you briefly feel lighter in your seat. Those moments last only a heartbeat, yet they offer a tiny glimpse of one of the universe's most beautiful ideas. Falling together creates the gentle illusion that gravity has disappeared. By now, the picture has become very different from the one we began with. Gravity is no longer simply an invisible pull. An orbit is no longer the opposite of falling. A curved path can, in the deepest sense, be perfectly straight. The universe has quietly invited us to exchange familiar words for deeper meanings. And perhaps the greatest surprise is still waiting. If Earth has been following this graceful path for more than 4.5 billion years, how has that extraordinary balance endured for so long? Why has our endless fall remained so remarkably steady, giving oceans time to form, continents time to drift, forests time to grow, and life itself enough time to awaken beneath the stars? That quiet question leads us back to the earliest days of our solar system, where the story of Earth's journey first began. If you could somehow travel backward through time, long before the first ocean reflected sunlight, before the first mountain rose above the horizon, before the Earth itself had fully formed, you would find a very different solar system. There would be no blue planet, no moon, no familiar continents. Instead, you would see an enormous cloud of gas and fine dust, stretching across billions of kilometers. At first glance, it might appear almost motionless. But appearances can be wonderfully deceptive. Like nearly everything we have explored tonight, what seems still is often quietly moving. That immense cloud was slowly turning. Not quickly, not dramatically, just enough that, Over millions of years, the entire cloud began to flatten into a vast spinning disk surrounding a young sun. It is difficult to imagine such immense stretches of time. Millions of years pass so slowly that they almost escape human intuition. Yet nature is rarely in a hurry. It shapes stars the way a river shapes stone, patiently, quietly, one gentle change at a time. Within that great rotating disk, tiny grains of dust occasionally drifted into one another. Most collisions were so soft that the grains simply clung together. Those small clusters attracted more material. Pebbles became larger bodies. Larger bodies gathered still more matter. Given enough time, those growing worlds slowly became the planets we know today. Earth was one of them. This means something rather beautiful. Our planet did not suddenly begin orbiting the sun after it was created. It was born moving. From its very first moments, Earth inherited the quiet rotation already present within the cloud that gave it life. In a sense, our planet never learned to orbit. It simply continued a journey that had begun long before Earth itself existed. That ancient motion has never completely disappeared. Even today, more than 4.5 billion years later, Earth still carries the gentle momentum of its birth. It is rather like a child who learns a favorite melody from a parent without ever remembering the first time it was heard. The song simply becomes part of who they are. Earth carries its own ancient melody through space. The sun's gravity did not erase that motion, it gently shaped it. Together, these two quiet influences created one of the most stable dances in nature. Imagine watching two skilled figure skaters gliding across fresh ice. Neither skater remains perfectly still. Every movement is answered by another. Each turn flows naturally into the next. There is no struggle, no sudden correction, only continuous balance. The beauty of the performance comes not from resisting motion, but from moving with it. Earth's journey around the sun possesses that same quiet elegance. Our planet is always moving forward. Gravity is always gently guiding that movement inward. Neither overwhelms the other. Instead, together they produce an orbit that has endured long enough for continents to drift, mountains to rise, forests to spread, and life to slowly discover countless new forms. When we draw Earth's orbit in books, it often appears as a perfect circle. That picture is wonderfully simple. It is also only part of the story. In reality, Earth's path is ever so slightly stretched. Rather than tracing a flawless circle, it follows a shape known as an ellipse. Fortunately, there is nothing complicated about that idea. Imagine placing two small pins into a sheet of paper and wrapping a loop of string around them. Now pull the string tight with a pencil and slowly draw. Instead of a perfect circle, a slightly stretched curve appears. That gentle shape is an ellipse. Earth's orbit is so close to being circular that, from our everyday perspective, the difference is almost impossible to notice. During one part of the year, our planet is a little closer to the sun. Several months later, it is a little farther away. The difference is surprisingly small compared with the enormous scale of the solar system. More importantly, it is not the reason we experience the seasons. Many people quietly assume that summer arrives because Earth moves closer to the sun. It is a perfectly reasonable guess. Yet the real explanation is even more fascinating. The seasons are created primarily because Earth's axis is tilted. As our planet travels around the sun, different parts of the world receive sunlight from slightly different angles throughout the year. That gentle tilt changes the length of days, the height of the sun in the sky, and the warmth reaching the surface. It is another reminder that the universe often prefers elegant explanations over obvious ones. Earth's orbit is also not as lonely as it first appears. Although the sun dominates the solar system, our planet is surrounded by many neighbors. Jupiter, Saturn, Venus, Mars, and the other worlds all possess gravity of their own. Each quietly influences the others. The effect is extraordinarily subtle. Nothing dramatic happens overnight. No planet suddenly changes direction. Instead, countless tiny gravitational nudges accumulate over immense spans of time. You might imagine an orchestra performing a slow, peaceful symphony. Each instrument has its own voice. The violin cannot ignore the cello. The flute does not play in complete isolation. Every sound blends with every other, creating a harmony far richer than any single instrument could produce alone. The solar system behaves in much the same way. Every planet contributes its own quiet note. Every orbit responds, ever so slightly, to the presence of its neighbors. It is a cosmic symphony that has been playing for billions of years. Sometimes people hear that planets influence one another and imagine a fragile system on the edge of collapse. The truth is almost the opposite. The solar system is remarkably resilient. Small changes happen continuously. They always have. Earth's orbit gently shifts over extraordinarily long periods. Its shape changes by tiny amounts. Its orientation slowly evolves. These changes unfold so gradually that entire civilizations rise and disavow stability. In nature does not mean perfect stillness. Very little in the universe remains absolutely unchanged. Stars slowly age, continents drift, galaxies move. Even atoms quietly exchange energy. Stability simply means that change happens slowly enough for larger patterns to endure. A mighty oak sways gently in the wind. Its branches move, its leaves flutter, yet the tree remains. A river never contains exactly the same water twice, yet the river keeps its familiar course. Earth's orbit is stable in much the same way. It is alive with tiny adjustments, yet its overall rhythm remains beautifully dependable. That dependable rhythm has made life possible. Without it, the climate of our world might change too quickly for ecosystems to adapt. The quiet regularity of the seasons, the predictable return of sunlight, and the long stretches of environmental stability that allowed complex life to flourish, all depend upon this remarkably graceful balance. It is humbling to realize that every forest, every coral reef, every bird that has ever crossed the sky, and every human story ever told has unfolded aboard a planet whose journey through space has remained astonishingly steady for billions of years. And yet, no balance in the universe exists entirely beyond change. However stable an orbit may be, it is never frozen forever. Even the most graceful dance could look very different if one step were ever so slightly altered. That thought invites a quiet exercise of the imagination, not to predict catastrophe, but to appreciate just how delicately our familiar world has been shaped by the path it follows around the sun. By now, Earth's journey around the sun no longer seems like a miracle that somehow escapes gravity. Instead, it feels like an elegant conversation between motion and the quiet shape of the universe. For billions of years, that conversation has unfolded with extraordinary consistency. Every sunrise, every changing season, every ocean tide, every generation that has ever lived has depended upon the remarkable steadiness of Earth's orbit. Once we begin to appreciate that balance, another gentle question naturally arises. What if the journey were just a little different? Not dramatically, not enough to send planets crashing together. Only a small change, a slightly different path around the sun. The universe often reminds us that enormous consequences can grow from surprisingly subtle beginnings. Imagine, for a moment, that Earth had been born traveling just a little more slowly, not by an amount you could ever notice in daily life, only enough that the sun's gravity could gradually guide our planet into a slightly smaller orbit. Year after year, Earth would travel a little closer to the sun. The change would not happen overnight. There would be no sudden blaze across the sky. Instead, sunlight would slowly become more intense. Oceans would lose water a little more quickly. The atmosphere would begin changing in quiet ways. Climate patterns that had remained familiar for millions of years would slowly shift. Nature almost always prefers gradual change to dramatic transformation. Now imagine the opposite. Suppose Earth had inherited just a little more forward motion during its birth. Its orbit would slowly settle farther from the Sun. The difference might seem almost insignificant on the scale of the solar system. Yet even small changes in the amount of sunlight reaching our planet could reshape the world over immense stretches of time. Winters might grow longer, ice could linger farther toward the equator. Regions that today support forests might instead become open plains or frozen landscapes. The remarkable diversity of life we know today might never have appeared in quite the same way. Perhaps this is one of the universe's quiet lessons. Life does not require perfection, but it does depend upon balance. Neither too close, nor too far, neither constant change, nor complete stillness. Earth has spent billions of years traveling through a remarkably gentle middle ground. Astronomers sometimes call this the habitable zone. The phrase may sound technical, but the idea is beautifully simple. It is the region around a star where temperatures can allow liquid water to remain on a planet's surface for long periods of time. Water may seem ordinary because it surrounds us every day. Yet throughout the known universe, it is something rather precious. Liquid water flows, it dissolves, it carries nutrients, it allows chemistry to unfold with extraordinary richness. Every known form of life depends upon it. Earth's orbit has helped keep that water in its liquid form for an astonishing span of time. Not perfectly. Ice ages have come and gone. Warm periods have risen and faded. Continents have rearranged themselves. But through all those changes, the planet remained within a range that allowed life to continue adapting. Our nearest planetary neighbors offer quiet reminders of how different that story might have been. Consider Venus. At first glance, Venus and Earth almost seem like siblings. They are similar in size, similar in composition, both formed from the same young solar system. Yet today they could hardly be more different. Beneath thick clouds, Venus is hot enough to melt lead. Its atmosphere traps heat with extraordinary efficiency, creating a warming process that feeds upon itself until the surface becomes unimaginably hostile. Scientists call this a runaway greenhouse effect. The name sounds dramatic, but the underlying idea is gentle enough to picture. Imagine placing a blanket over yourself on a cool evening. The blanket traps some of your body heat, making you more comfortable. Now imagine adding another blanket, then another, and another. Eventually, instead of comfort, the trapped warmth becomes overwhelming. Venus experienced something similar on a planetary scale. Its atmosphere gradually held onto more and more heat until the process reinforced itself. The result was not a sudden disaster. It was a slow transformation unfolding across immense spans of time. Mars tells a different story. It orbits farther from the Sun than Earth. Long ago, evidence suggests that rivers once flowed across its surface. Lakes may have shimmered beneath an ancient sky. Today, however, Mars is a much colder and drier world. Much of its remaining water is locked away as ice or hidden beneath the surface. Standing between these two neighboring planets, Earth begins to seem even more remarkable. Not because it escaped the laws of nature, but because those very laws produced conditions that remained favorable for life over extraordinary lengths of time. There is another gentle possibility worth imagining. Earth's orbit could remain at nearly the same average distance from the Sun, while becoming slightly more stretched. Instead of following its current nearly circular path, the planet would spend part of each year much closer to the Sun and another part much farther away. The seasons, already shaped by Earth's tilted axis, would become far more extreme. Summers could grow much hotter, winters much colder. Many plants and animals that have adapted to today's relatively stable rhythm might struggle to keep pace with those changing conditions. Again, the change would not necessarily arrive all at once. Nature often rewrites its stories one quiet chapter at a time. Even beyond our own solar system, astronomers have discovered wandering worlds that travel alone through the darkness between the stars. These are sometimes called rogue planets. Unlike Earth, they no longer circle a parent star. Instead, they drift through interstellar space, carrying whatever history remains from distant gravitational encounters long ago. It is a strangely beautiful image, a lonely world moving through endless darkness. No sunrise, no familiar year, only the quiet journey itself. Fortunately, Earth's story has been very different. For billions of years, our planet has remained part of a stable family of worlds orbiting the same star. Jupiter's enormous gravity has helped shape the architecture of the solar system. The other planets contribute their own subtle influences. Together, they have maintained an intricate balance that has endured far longer than any mountain, any ocean, or any living species. When we think about Earth's orbit, it is tempting to imagine it as a fixed circle drawn permanently into space. But the universe rarely creates perfect stillness. Instead, it creates rhythms, gentle adjustments, tiny corrections unfolding across spans of time so vast that they are almost impossible for a single human lifetime to notice. Perhaps that is why our original question now feels quietly transformed. Instead of asking why Earth does not fall into the sun, we begin to appreciate something even more profound. Our world has spent billions of years following an extraordinarily graceful path, not because it is somehow protected from gravity, but because gravity itself has guided that journey with remarkable consistency. And perhaps the greatest wonder is not that Earth continues to fall, it is that this endless fall has become the foundation upon which every forest, every ocean, every civilization, and every human life has quietly unfolded. As our journey gently draws toward its close, it is worth returning to the simple question that first invited us here. Why doesn't Earth fall into the sun? It seems such a straightforward mystery, almost the sort of question a curious child might ask while looking up at the sky. Yet, like many of the universe's most beautiful questions, its simplicity concealed extraordinary depth. Along the way, we discovered something unexpected. The question itself was quietly leading us in the wrong direction. Earth does not avoid falling. Earth has never escaped gravity. Earth has never hovered motionless in space. Instead, our planet has been falling from the very beginning, not for days, not for centuries, but for more than 4.5 billion years. It is a fall unlike anything we experience in everyday life. A fall with no sudden impact, no final destination, no dramatic ending. Only an endless journey around a star that has patiently illuminated our world since long before the first living cell appeared. Perhaps this changes the way we think about gravity itself. For much of history, gravity seemed almost like an invisible hand, constantly reaching across empty space, pulling one object toward another. That picture served humanity remarkably well. It helped explain the movements of planets. It guided explorers of the heavens. It allowed spacecraft to travel to distant worlds with astonishing precision. Then Einstein invited us to look a little deeper. Rather than imagining gravity as an invisible force stretching across emptiness, he asked us to imagine that the universe itself possesses shape. The sun quietly changes that shape. Earth quietly follows it. What we call gravity may simply be the natural consequence of moving through a landscape far richer than our senses can directly perceive. There is something quietly comforting around. The universe no longer feels like a collection of horse-tomatids. Instead, everything is connected. Stars influence planets. Planets guide moons. Galaxies shape one another across unimaginable distances. Even light, which we often imagine traveling in perfectly straight lines, gently follows the contours of this vast cosmic landscape. In ways both subtle and profound, everything participates in the same grand geometry. And yet, Despite all that humanity has learned, gravity still keeps some of its deepest secrets. Modern physics can predict its effects with extraordinary accuracy. We can calculate the paths of planets centuries into the future. We can guide robotic explorers across billions of kilometers. We can detect tiny ripples passing through the fabric of the universe itself. Yet one mystery remains quietly unsolved. Why does gravity exist in the first place? What is its deepest origin? Scientists continue searching for answers. Some explore the possibility that gravity may eventually be united with the other fundamental interactions of nature. Others investigate whether space itself emerges from even more fundamental structures hidden beneath our current understanding. These ideas remain active areas of research, reminding us that science is never simply a collection of finished answers. It is an ongoing conversation with the universe. Each generation listens a little more carefully. Each generation discovers that the horizon of knowledge has quietly moved farther away. There is something rather beautiful about that. The more we learn, the more wonder seems to grow. Perhaps that is one of science's greatest gifts. It does not diminish mystery, it transforms mystery into curiosity. And curiosity, unlike uncertainty, is peaceful. It invites us to keep looking, to keep asking, to keep appreciating the quiet elegance of a universe that is often far more imaginative than our first assumptions. Think for a moment about everything that depends upon Earth's graceful orbit. Every sunrise you have ever watched, every autumn leaf drifting gently through cool air, every child learning to walk, every bird crossing the morning sky, every forest growing one ring wider each year, every conversation shared beneath the stars. All of these moments have unfolded because our planet has followed an extraordinarily stable path through space. Not a perfect path, not an unchanging one, but one balanced with remarkable delicacy across billions of years. Sometimes when we imagine the universe, we picture dramatic explosions, brilliant supernovas, enormous black holes, or galaxies colliding across unimaginable distances. Those events are certainly real. They remind us that the cosmos can be astonishingly energetic. Yet there is another side to the universe, a quieter side, one built not upon violence, but upon rhythm, upon patience, upon delicate balances maintained across immense spans of time. Earth's orbit belongs to that quieter story. It is not spectacular because it changes suddenly. It is extraordinary because it has remained so beautifully dependable. Tonight, as you rest, perhaps it is comforting to remember that nothing beneath you is truly standing still. Your home is moving, your city is moving, the mountains, the oceans, the clouds drifting overhead, all are quietly traveling together aboard a planet that continues its ancient journey around the sun. You are not watching the universe from a fixed place. You are already part of its motion, part of its story, part of an endless voyage that began long before humanity appeared and will continue long after our own brief moment has passed. And somehow, despite all that movement, the experience of life here remains wonderfully calm. Perhaps that is the greatest surprise of all. The deepest stability is not always found in stillness. Sometimes it is found within motion so graceful that it feels perfectly at peace. As the night grows quieter and the stars continue their silent journeys overhead, you may find yourself looking at the sky a little differently, not as a ceiling above the world, but as the vast ocean through which our small blue planet has been gently sailing all along, a world forever following the quiet contours of the universe, forever falling, forever moving, and, through that endless and beautiful journey, forever giving life a place to call home. Thank you for joining me on this quiet exploration tonight. Wherever your thoughts may wander from here, I hope they do so with a little more wonder, a little more peace, and a quiet appreciation for the remarkable journey that has been carrying you every moment of your life. And if, somewhere along the way, sleep has already begun to find you, then may your dreams be as gentle as the path our planet has followed beneath the stars for billions of years. Good night.